clear. All right. Well, thank you for having me. I'm very happy to be here. I feel like coming back home. I used to be a postdoc not until long ago, just across the street in Cuba. But I've since moved to Imperial College London. And actually, the work that I'll tell you about started when it's based on a paper I wrote myself, and then a paper with Chris. And mostly what I'm going to tell you about today is this paper, which hopefully will appear still in May 22. Fingers crossed. All right, so I'm going to report on this result, which is on the title. So you already know the main punchline of the talk. That's what the result is, but hopefully it will make sense to you. So, all right, so what is the homology problem? So I'm not going to assume that you're familiar with this. The homology problem is the following. So I'll describe it vague terms first. So you're giving us an input, a simplicial complex, which I'll describe soon what it is, but it's basically a triangulation of a space, or a higher dimensional triangulation of a space. And you have to think how to input this in some efficient way, but I'll get to that later. And the output of the algorithm should be the number of I-dimensional holes of the simplicial complex. So for here, for example, we have one-dimensional hole. So what is the dimension of a hole? Dimension of a hole is, confusingly enough, is the dimension of the space bounding the hole. Okay, so here we have a one-dimensional hole because this red cycle is enclosing something which is empty. So if this space were to be filled in, that would not be a hole. Okay, but because it isn't, it is a hole. Now here you have a two-dimensional hole because that tetrahedron inside is empty. Okay, so you give sigma as an input, and the output should be the number of holes of different dimensions. Now, the study of homology is like a really old classical subject in mathematics that goes all the way back to Poincaré, another in the 1800s. So it's very old-fashioned classical math. However, as a computational problem, even though the problem of homology is very natural, it was not posed formally as a computational problem until 2002, 20 years ago, in fact, this February, in this very nice kind of collection of problems that were proposed by these two authors in this paper, Some Algorithmic Problems in Polytope Theory. So there are 35 problems there, and this one is problem 33. Okay. And all right, so we're going to consider the decision version of the problem, where you're given a simplicial complex sigma, and you have to answer that question: is there an I-dimensional hole? Yes or no. So I is part of the input, the integer. Okay.
Maybe for intuition, like, is there some special case that's easy to understand? Like, for example, one dimension is 2, and does it have like counting some kind of cycles in the graph or something?
Well, you're counting holes, so they're not exact. Yes, we'll get some very concrete examples, but yes, absolutely.
I'm a little bit puzzled by the way you count dimensions.
Yes, it's very confusing. I would. Yes, it's very confusing. So if the boundary is one-dimensional, you say that is a one-dimensional hole, even though the space inside will be two-dimensional.
But the space inside is the thing which is absent.
Yes, I agree. I agree. There are endless discussions about this. But, what can I say? This is the terminology. There's some reasons for it. Okay. So it was only in 2016 that this problem was shown to be NP-hard. So this was suspected at the time that it will be NP-hard. But so this was a nice result, but didn't come much as a surprise, because kind of expected. So no offense, but you know, it was still hard to prove, but it's something that you would expect. Okay. Now, what was not entirely clear was whether the problem is contained in NP or not. Okay, so in some cases it is, in some special instances. In general, it seems like it isn't. So not completely clear exactly what the hardness of this problem is. So it's NP-hard, so it's it's hard, but how far up is it? Okay.
Good question.
Yeah.
Is there some clear relation between the decision version and the computational version? As in, like, if you can solve the decision version, then the computational isn't just polynomially.
Yeah. I'll comment on this. So we're considering the decision version of the problem. The original version of the problem is counting.
Okay.
So the hardness of the counting problem will be determined by the hardness of the decision problem. Yeah.
Your first slide went extremely quickly. Could you repeat how the input sigma is given?
I'll give you more details next. I was deliberately vague about it.
So are you going to explain how you describe the
Yes,
instances?
yes, 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 hopefully to your satisfaction, yes.
Also a question, so why can you not just, why is it not in NP? Because it seems like if you get some pointer to an I-dimensional hole, then you just check it's an I-dimensional hole.
Well, the answer is that it's not obviously in NP, because when you triangulate a space, the boundary of a hole is given by a collection of all the little simplices that surround the hole. Okay, it's not just one. And this combination could be exponentially large. Okay, so even though, for example, you may have a simplicial complex of dimension n, but the number of triangles that compose it could be 2 to the n. And you have to give the linear combination of those 2 to the n simplices that surround the hole.
Okay, but for like one-dimensional?
Yeah, for one-dimensional, nothing is hard, right? I mean, yeah. So this is a question about scaling with the number of vertices in the simplicial complex.
There's still
I think this is what we come up
something
with.
about the way you specify the instances,
Yeah.
because if you simply list all the
Yes,
simplices,
this
then
will become clear.
this can't be the problem.
Yes. So I'll get to this. I think it will become clear. If not, ask me again. Okay.
Can I ask another question? It is at least in p-space, I would think, right?
I believe so. Yes. Okay. So why are we interested in this question? So first of all, as I said, it's a fundamental problem in computational topology whose complexity is not known. The second is that it's of practical interest, so it's not a purely academic interest. So it relates to the technique of topological data analysis. How hard is it to extract topological information out of large data sets? Okay, so you're given like a point cloud, like a cloud of points of data that are typically high dimensional. And one of the techniques that people use to analyze the data is to extract topological information from this cloud. Okay, and that relates to understanding the topology of the spaces and in particular holes, different dimensions.
So what is the utility of this topological information in the practical context?
So there are many different applications. So for example, here, this is an example of, there's some data of patients that have diabetes, and you perform some data analysis to kind of, to find different clusterings of how patients are affected by the disease and so on. So there are many techniques for analyzing data, but topological data analysis kind of tries to extract some information which is underlying to the system, which is not sensitive to noise, for example. That's the reason why it's useful. And it's a very compact description, right? So it loses information, so it dimensionally reduces the data, but it maintains information which is, kind of essential. All right, and finally, the other reason is that there's an efficient quantum algorithm for estimating the number of holes. So this is not the exact counting problem, because as we'll see, that's very hard. But if you want to approximately estimate the so-called Betty numbers, which is the number of holes, relative to the dimension of the spaces, this is kind of crucial that you can do this. This normalization factor is crucial, so you can do it efficiently, and to additive approximation. Okay, so it's not fantastic, but it's something. And as far as people know, there's no classical algorithm that achieves the same. Okay, so this is a quantum algorithm by Lloyd and collaborators from 2014, and is under certain conditions efficient. And Chris here in the audience has studied this and was one of my motivations for this work. Okay, yeah. So as I said, one of the questions we'd like to answer is, can this quantum algorithm by Lloyd and collaborators be dequantized? So this issue of topological data analysis is something that is used in machine learning, for example. And algorithms in machine learning have been, dequantized recently. People are getting increasingly worried that everything's going to be dequantized. We want to argue, although I won't give you a proof, but we think pretty solid evidence that this algorithm cannot be dequantized. Okay, that it will follow from the complexity results that I'll discuss.
What is the star? Is there some issue?
Sorry.
What is the star of the efficient?
Yes, it's so I can hide all the fine print about this when this algorithm is efficient and when it isn't. So it is efficient under certain conditions, and it's not entirely clear that under those conditions there's no classical algorithm that will do the same job. Still, we think that that's indeed it cannot be dequantized. All right. So my main point of the talk here, if you remember one thing, like the slogan is homology is quantum mechanical. Okay, it's really an intrinsically quantum mechanical problem. And so, as I said, it was suspected this problem was NP hard. So this is NP, and this parabola here is NP hard. So it was not known where it was sitting in this vertical space. But what I want to argue is that it sits exactly here, squeezed between these two quantum complexity classes, QMA and QMA1. Okay. Now, as you know, for quantum complexity classes, you usually define promise versions of the problem. So what I'm going to show is that the original problem of homology is QMA1 hard. And if you provide an appropriate promise for the problem, it has to do with the spectral gap of a certain operator, you can place a problem inside QMA. Okay, and it's a very natural promise to consider. Hopefully, I'll persuade you of that. Okay, so this does much better. It's a much better lower bound than NP, and it also gives an upper bound to the complexity of the problem. So let me remind you very vaguely what is QMA. So QMA is a class of problems with the same complexity as finding ground states of local Hamiltonians. Okay, give a more precise definition later, but for now, to make my point, this is the definition of QMA. And QMA1 is a class of problems. Yeah.
It's all about finding the ground state. It's about approximating the ground state energy.
Absolutely.
It's
Yes.
actually a much simpler problem, also one that you can state classically.
Yes.
Because
That's what I
the
mean.
ground state is not a problem.
Yes. Approximating the lowest eigenvalue for local Hamiltonian. Yeah. Or deciding if it's above or below a certain threshold. Yes. Now QMA1 is a class of problems with the same complexity as deciding if a Hamiltonian is frustration-free. So what does frustration-free mean? Is to decide whether the ground state of the full Hamiltonian is also a minimum of each of these components here. Okay, so if each of these components, which is just interacting with some local degrees of freedom, is minimized in the whole state, then you say that Hamiltonian is frustration-free. And the homology problem sits exactly between these two classes.
Okay, Marcos,
Yeah.
and what's the complexity definition of QMA1?
We'll get to it. I'll give you the precise definition soon, but it's perfect completeness QMA.
Oh, the one stands for the.
The one stands for perfect completeness. Completeness,
Yeah.
perfect completeness. So in the case of yes instances, you accept the probability one. Okay, so why is homology quantum mechanical? Why does it have to do with finding complexity of finding ground states? And the reason, the underlying reason ultimately goes back to an old paper by Ed Witten in 1982, where he pointed out that the ground states of supersymmetric quantum mechanical systems are in one-to-one correspondence with elements of homology. Okay. So this was an old and very famous paper, and it follows from this connection that the complexity of homology is equal to the complexity of finding supersymmetric ground states. I won't go too much into what a supersymmetric system is, but let me just say that a supersymmetric system is a system that has special kind of symmetries. Okay, so physicists like it because you can usually solve things. Okay. All right, so if you knew what the complexity of finding supersymmetric ground states is, then you know what the complexity of homology is. And if you know about the complexity of homology is, you will know this. The problem is that none of these questions were studied in the literature until we embarked with Chris about a year ago, now almost a year and a half, to answer this question. Okay.
So, like in this context, what is the homology over? Is it like some reals or integers?
Well, so the natural correspondence here will be over the complex numbers because we're doing quantum mechanics. Yeah. But if you do quantum computation, you may want to take just the real numbers. That's fine. Yeah. Okay. So let me just mention briefly in passing that there's a well-known, I know it's known to all of you, that there's a deep relation between topology and quantum computing. And this comes through the study of certain physical systems that are topological. They're called topological quantum field theories. So these are systems which we believe are realized in nature and condensed matter systems, but they have a very nice mathematical structure that can be axiomatized as quantum field theories, which is not true about other quantum field theories. But we think of it as a theoretical physicist, I think of it as a physical system. And so it was pointed out by Witten in '89 that there's a relation between knot theory and these topological quantum field theories. Okay, and this is what ultimately led to his Fields medal. This relation, that there's some physical systems whose certain partition functions capture something called the Jones polynomial of these knots. Okay. On the other hand, Friedman and collaborators, using ideas from topological quantum field theory and axiomatic formulation, came up with a new model of quantum computation that turned out to be equivalent to the circuit model, but it's a different way of thinking about quantum computation. And so my point here is that these physical systems connect and give an integral relation between questions in topology and aspects of quantum computation. And the situation here is a little bit similar. So we have these other physical systems, which are supersymmetric. They have this special symmetry. They relate to homology, again, by the work of Witten, and this will lead to the connection with quantum computation. So it's another area where there's a natural connection. Comes again from physics. So taking this into account, the set of ideas with Chris, we propose to consider a field that you may call quantum computational homology, which arises at the intersection of these three circles here. So it'll be the study of many body systems, computational complexity, and supersymmetry. And the claim is that here in this intersection, there is this field called quantum computational complexity, which you can define as to be the field which uses methods of supersymmetric Hamiltonian complexity to study homology, okay, or problems in computational topology. So in this talk, I'll give you a first example of the most fundamental problem in this intersection, which is the homology problem and how to find its complexity. So I'm going to first tell you about simplicial homology, then I'll tell you about QMA and quantum K-set, just review those. And then finally, I'll discuss our reduction, the proof hardness of the homology problem. Okay, so let's start with simplicial homology. So the basic building blocks are simplices. So they have zero simplex, which is a point, a one simplex, which is a line segment. I'm going to take here simplices to be oriented. So they have a line. Two simplex is a filled-in triangle. Three simplex is a filled-in pyramid, tetrahedron, really, and so on. And so a notation which is standard is, so if this is a point x naught, so you can think of these as points in Rn. Okay, so zero simplex will be just characterized by the single vertex, two vertices, and so on. And so a simplicial complex is obtained by gluing these simplices. So here, for once in topology, terminology makes sense. So this is a simplex and this is a complex. Okay, so the main star in homology is the boundary operator, so-called boundary operator. So the boundary operator, denoted by this del, is defined by how it acts on simplices. Let me just give you an example. So it's a map from simplices, in this case, one simplices down to zero simplices, and it's defined to act in this way. Okay, so if you act with this on this one simplex, it gives you the difference between the two endpoints. Okay, so which indeed is that these 2 points are the boundary of the simplex. Okay, and you put this kind of mysterious minus sign in between for reasons that will become clear. Okay, let's do the next one. So consider two simplex. So it's a two-dimensional triangle bounded by these three edges. So you act. So if you want, by definition, the boundary of this triangle will be these three segments. Again, you put some mysterious minus sign, and you see that the minus sign works such that you can think of this minus sign. What it's really doing is reversing the orientation of this edge. So when you reverse the orientation, you can put them all together, and you get this object. So this is all very formal. Okay, so it's formal sums and so on. And indeed, this is the boundary of this solid triangle. Okay, so in general, using the notation that I wrote before, the way that a boundary operator acts on a P simplex is just kind of goes around deleting one vertex out of the set and putting alternating signs in front. Okay, so you can see here, for example, that's how it works. So the first guy, you omitted the 1, here you omitted the 2, here you omitted the 3, and you have alternating signs. Okay, why is this a reasonable definition? Ask me questions if you're.
Yeah, what do these minuses do?
Yeah, exactly.
It's not like a subtractor, like in the first one you take
So,
the points and you take the difference of these two vectors, but it's something else.
Yeah, the main reason is that something which is closed will have no boundary, because then you go all around and the alternating signs will give you 0.
Okay.
That's the
It
reason.
seems like it's reversing sort of these arrows.
Yeah.
And in the other case, it reversed these 2 points.
Yes. Zero-dimensional holes are hard to get you wrap your head around. Yes, but I'll show you now. So indeed, so why do you put these minus signs? Is because of closed loops. For example, this. So this is not filled in. This is just a closed loop. Okay. What is the boundary of this? Is the boundary of this? So this is a linear operator. So it's the boundary of this one simplex plus the boundary of this one simplex plus the boundary of this one simplex. Using the signs from before, you see there's this cancellation. So you get 0. Okay, which is what you expect. The second important property that follows from the signs is that the square of the boundary operator vanishes, which means that a boundary has no boundary. Okay, that's the algebraic manifestation of the fact that intuitively something which is a boundary doesn't have a boundary. So for example, take this. So take the solid, the filled-in triangle, and take the boundary of it. Well, you take the first boundary, you get this, the boundary of the triangle, and the boundary of this you already saw was 0. Okay, and you can work it out. It works for any simplex. Okay. Okay. So what is a hole? A hole is defined in terms of this boundary operator. So a hole here, I have an example of one-dimensional hole and two-dimensional hole. We see that holes have this property that first, they don't have a boundary. So this is a closed loop. It's called a cycle. This will be a 1 cycle, and this will be a 2 cycle because it's not filled in. So it has no boundary, meaning that the boundary operator acting on that hole, that's I'm denoting by C, isn't the kernel of this operator. Second, it is not itself the boundary of something else. For example, this one-dimensional hole here is not the boundary of this triangle because the triangle is not filled in.
And sorry, before in the simplex, you used to have some arrows.
Yeah,
And
I'm omitting the arrows here, but they should be there. Well, yeah, they should be there. Everything is oriented and minus signs are important. Okay, so, and furthermore, the hole is not the boundary of something else, because if I were to fill this triangle in, then the red line will be the boundary of that filled in triangle, and it will not be a hole.
And del squared is 0 on complexes also.
On complexes?
Yeah,
What do you mean?
like when you act with del squared on that complex that you somehow brought together by.
Well, you don't
So-
act on the complex, you act on the simplices. Yes. Okay, I'll formalize this a little more soon. Okay, so the structure that we have here is actually the structure of an abelian group. Okay, so before going into the structure of the abelian group, let me say the following. So if you have an operator del which squares to 0, it's nilpotent of degree 2, then it makes sense to define the following. So you take the kernel mod out by the image. So if you go back here, what we're doing is taking all the things which have no boundary but are not themselves the boundary of something else. That's what a hole is. It has no boundary, but it's not the boundary of something else. So this is what is going to capture the notion of a hole. So if you want to think of it in this way, like in terms of like linear algebra, you have an operator whose image is contained inside its kernel. But it's not always true for a general operator, but it's true for a nilpotent operator. Okay, that the image is contained in the kernel. Then it makes sense to take this cosine. Okay, and the homology is whatever is left, which may or may not be 0. Okay, that's how the homology is defined. It's a difference between the space in between the image and the kernel. Okay, and this is called a homology group of del. Okay, so now we can be a little more precise. The precision will increase as we go along. What the homology problem is. So the homology problem is you're given a boundary operator, and this C should be actually a sigma, simplicial complex. Sorry for that. So you're given, still I haven't answered the question of how you specify the sigma. I'll get to it. So you specify the simplicial complex, you specify the boundary operator, and the question is the homology group trivial or not trivial? Okay. If it's not trivial, that means that there are things which are holes because they're closed, but they're not the boundary of something else. And otherwise, no. Okay, so to be a little more specific, so the way this is all more formally defined is by considering the notion of a chain complex. So you're given a simplicial complex sigma, and what you do is you break it down into a collection of abelian groups. And these abelian groups, the generators for these abelian groups will be all the simplices of different dimensions. So C sub k will be the space, the space spanned by all the simplices of dimension k inside your complex. Okay, and so you consider all that 0 simplices, all 1 simplices, and so on, all up to n simplices. So n is a number of vertices in your graph. Yeah, in your simplex.
I do not understand how does the simplices act on each other? Like, what's the multiplication of this?
So the multiplication is really an addition. Okay, so it's a abelian group, and it acts in the way that I showed before. For example, you have the boundary operator. You take the boundary of the triangle. You get the alternating sum of 3 things, right? You flip the minus. You turn the minus into a plus by flipping the orientation, and then you sum them by just putting them all together, overlapping the vertices, and that's the addition of the group. And it's clearly abelian, okay, and it's finite. And finite abelian groups are classified, and so we know everything. Still need to compute it though. Okay. So, all right. So once you have these spaces, abelian groups, what you do is you stitch them together by the action of this boundary operator. Okay, so here I've written a subscript for the boundary operators. It's all part of the same boundary operator. It's just different blocks of it. So the block of the boundary operator acting on two simplices is represented by del 2. And that will give you an element of C1, which will be some linear combination of the one simplices. Okay, so this is just a formalization saying that a two-dimensional triangle, for example, will give you some linear combination of edges and so on. Okay. Now, when you have the structure that's called chain complex, oh, I forgot to say, so what the important property that del squares 0, but the boundary has no boundary, is written in this notation, in this form. So if you act with two consecutive boundary operators, you get 0. Okay. Okay, and now you can define the homology group at each level. Okay, because again, the image of this guy is contained inside the kernel of this. So you can take the coset, and this is defined to be the kth homology group. So the kth homology group. So this is what defines a k-dimensional whole. You look at a specific point in this chain, and all the things which have the dimension, which are close but not the boundary of something, that's a whole of dimension k. Okay. Otherwise, you have to be saying it's dimension k plus 1, and that's one of the reasons why you define the whole to be this way. Okay. It's going to bite you somewhere. The definition of plus or minus 1 is going to be something. Okay, so the Betty numbers are defined to be the rank of these groups. Okay, so how many generators? They're free abelian groups, so the number of generators in the group.
Oh, sorry, in which way is a group? What's the group action again?
Yeah, that's what the question before. So it's just a simple addition of simplices.
No, for the homology group.
It's the same. It inherits. So the operator del, the boundary operator is really a homomorphism that respects the addition of the group. It preserves it. So even in the coset, you still have this structure, which is compatible with the boundary operator.
What are your scalars, the complex numbers here?
Yes, so you can use different coefficients here. So the most natural definition in this context is to use integers, positive and negative integers, because we'll do quantum mechanics. I'll be using complex numbers, but yeah, you can do either. Yeah. Okay, so I want to tell you about a particular complex, a particular simplicial complex that is specified, and this goes to the question of how do you specify the input by a graph. Okay, so given a graph, you can construct a complex, a simplicial complex. Okay, and it works this way. So you're given a graph G, and for example, this one, and you're instructed to find all k independent sets. So what are independent sets? Independent sets are subsets of the vertices that are disconnected from each other. Okay, so one independent set suggests you choose one vertex, for example, this one, or this one, or this one. So there are as many one independent sets as vertices in the graph. Two independent sets, you choose pairs of vertices. So here I draw a couple. And three independent sets, you choose 3, which in this case is just 1, and there's no 4 independent sets. Okay, so this structure ends there for this graph. Okay, so now the rule of the game is that to each k independent set, you associate a k simplex. How? Just by saying, well, those vertices that I chose from the graph define a simplex. Now I think of it as, I think the convex hull of these points that defines some tetrahedron or whatever triangle it is, and that is my simplex. And this space C sub k that I wrote before, this is called the space of k chains, is spanned by all k independent sets of G. Yeah.
Basically have in mind some mapping of the vertices to some d-dimensional space so that you can
Yeah. You have to embed all this in some high enough dimensional space so that everything fits. Yes, and then you take the convex hull of those points and that defines your object.
When you say span, do you mean convex hull or do you mean span?
No, I mean each one of them, each one of the elements here, each k independent set, I think of it as a collection of points in Rn, let's say. I take the convex hull of that defines a solid object, which I think of it as an abstract object, and then I can take the span of all such objects. Those are the generators of my group.
This is not a span in linear algebra, but some other span.
It's a span, yeah. I mean, in the sense of, like it's the same. Think of the abelian group as a vector space.
This is a span in terms of sort of gluing together.
No, in terms of adding things. Well, in some sense, as I was doing before, adding the arrows to make the triangle. Yeah, in that sense. Not gluing in the sense of I can glue a tetrahedron to to a line, for example, by joining the end of the line to the apex of the triangle. But that's when you can construct the complex. Here I'm just putting things together the same dimension. And take arbitrary linear combinations of those things.
What dimension do you need? Is it just a number of vertices or is it very different?
So so K will go from 0 up to the number of vertices. So I have a collection of chain spaces or abelian groups from K equals 0 to N.
But to take the convex hull, you need to associate your vertices with points in some d-dimensional space.
That's right. That's some other d-dimensional space that I make large enough so I can fit all the points.
So what is large enough d?
It has to be greater than N, I believe, greater or equal than N.
And being the number of vertices.
And be the number of vertices. Yeah.
Another question?
Yeah. Yeah.
So this is a very compressed, potentially compressed way of describing this object, right? Because
Yeah.
it can have exponentially many.
Absolutely.
Like when
Absolutely.
K gets like
Yeah.
over 2 or something, then you have the
Absolutely.
largest amount of.
Yeah. So you have
So-
N vertices. Sorry. Go ahead.
Yeah. So why this particular way of representing?
Yeah. So this
thing?
well.
Seems a bit.
So this is the problem that arises, for example, in topological data analysis. So if you want, that's the motivation from the practical point of view.
Okay.
That you have a bunch of points, and if you look at it from far away, it looks like kind of a cloud of points. But how do you? So what you will like to do is to triangulate the space that is like this cloud. So what you do is you take a point and you throw a ball of size epsilon around the ball, and as soon as it reaches another point, that if the two of them fall inside the ball of size epsilon, you connect them by an edge. So this defines a graph. Okay. And then the independence, or rather the clique complex, which I'll describe soon, is the triangulation corresponding to this underlying space.
Is it sort of like a one-dimensional projection of this?
It's the one
larger
skeleton. It's called the one skeleton of the simplified complex. Yeah. Anyway, I mean, from the abstract theoretical point of view, it's just a very natural thing to do because cliques or independent sets are things that one likes to count them, and they have nice properties, but they have this additional structure of abelian groups and so on. Okay.
They're also hard objects.
They're also hard objects, which is, so if you do complexity theory, then you like it. If you do algorithms, you don't like it. But I guess, yeah. Anyway, so you make this chain. So this is the zero simplex is just you choose nothing. So this really should be empty, but I mean that you choose nothing from the graph. You choose all one vertices, you choose all two vertices, and so on. And then you cannot choose n vertices. There's no n independent set because, well, unless the graph is completely disconnected. Okay. So if it's disconnected, then you use the empty. Okay. So you act with the boundary operator in the way that I said before. Let me give you an example so that to bring it down to earth. So consider this graph, which is two disconnected triangles. Why do I consider disconnected graph? Well, because it'll be relevant later. But so let's consider this case. So let's look at one independent sets. So that's just the vertices. So there's 6 elements. And let's look at 2 independent sets. So I can choose one vertex from here, but then no other from this triangle. I have to choose from another one because they cannot be connected. So they're 9. Okay. So what's the simplex associated, the complex associated to this? So I'll denote it by sigma 2 in this case, is the independence complex associated to G2, which is this graph here. And it's this. This is just a graphical summary of this data here. So I have my 6 vertices, which are my 6 one simplices. And then I have edges that connect, for example, A1 to B2, which is not listed here. Okay, X1, X2, which is this one of those 2 simplices. Okay. So this is the independence complex of G2. You see that this is connected even though this is disconnected. This is precisely because you're choosing independent sets from the disconnected components that are connected. And one more, just not to get confused. So it turns out in this simple case that this simplicial complex is a graph because there are no 3 independent sets. Okay, if I add another triangle, there will be 3 independent sets, and then I'll start having triangles, tetrahedron, and so on. Okay, so don't confuse this graph with this graph.
Shouldn't it be directed? Like, is there?
Yes,
what's the?
It should be directed. I omitted. Well, it should be directed once. So I'll have to choose an ordering of these guys, and that will define an orientation for the simplex. But I'll be careful later with the orientations, which are very important. Okay, so one final thing to notice about this simplicial complex is that it has 4 one-dimensional holes. You can see here, 1, 2, and then 3 here, and then 4 here. Okay, so in fact, if you compute the homology, you'll find that, well, I'll tell you later. If you compute the homology, you'll find exactly that it works out. Okay, but you can just see it from the picture that has 4 independent one-dimensional holes.
Can you do that again?
The hole, yeah. So this is a hole. This is a one-dimensional hole.
Ah, okay, yeah,
This is another one.
Yeah.
The other one is this kind of handle here, and the other one is this handle here.
I got it.
Any other one that you can imagine is a linear combination of these. So they're infinitely many holes, but they're spanned by 4 elements. In that sense, that's how we count holes. Okay, so the title of my talk was the click complex, and the click. Yeah.
One more question. Is this also dependent on the orientation that you put on the graph?
Not the number of holes. Yeah, you can choose different orientations, it'll be the same.
Interesting about that, like if you have a specific orientation such that the hole doesn't have like say like consecutive, let's say.
No,
like,
it has to.
It has to have.
Well, so
like,
okay,
consistent.
okay. So there are orientable simplices and non-orientable simplices, and here I'm considering only orientable simplices. And then as you go around, all the arrows match, and everybody's happy. But you can do crazy stuff. Yeah. Okay,
so I'm
so
sorry, the k-independent complex, whatever, is guaranteed to be orientable or not?
good question. I believe so, but I'm not 100% sure. I believe so. I don't have a clue. Okay, so what is a click complex? Because that was in my title after all. I'm not going to talk about the click complex much. It is built also in terms of a graph. Okay, but instead of considering independent sets, you consider clicks. So click is kind of the complement of an independent set. You consider subsets of vertices which are all interconnected with one another. Okay, to form a complete graph of size k. Okay. Now, the independence complex, I think you can believe it, of a graph G is the same as the click complex of the complement graph. Okay, so it's the same. Okay, so it's easier for me to work with independent sets. I'll work with independent sets. Okay, so going back to the question about the input. So the input to the problem will be the graph G, and the size of the input will be the number of vertices. So you can input the graph by, say, the incidence matrix. Okay, so now you say, well, but homology is just linear algebra. There's nothing to this problem. I mean, big deal.
That also means you're not considering arbitrary simplicial complex.
That's correct. That's correct.
Given as a geometrical object with only a special class.
That's correct.
Which can be inferred from such a graph.
Yes, yes. I do that for 2 reasons. One of them is because there's an efficient, clean description of how to input the simplicial complex, but also because it's a very special class of simplicial complexes, which will make our hardness result better than if I take an arbitrary simplicial complex. Because it's a restricted class of instances that we're considering.
It doesn't say something, if you don't have the special representation, then you could be forced to represent the simplicial complex just as a list of.
If you do that, none of this is hard.
Could be much easier.
If you do that, all this you just have to diagonalize. So if you have a simplex with m made out of, so you have a complex made out of m simplices, what you have to do is some operations with m by n matrices. So all this is, nothing is hard if m is small. The point is that in many applications and in many natural settings, m can be exponentially large. And then we have to deal with it. So if you give the entire complex as an input, then all this is true. The same is true about the Hilbert space, right? If you just give dumping the Hilbert space into the list of the entire Hilbert space, and find the ground state is easy. Yeah.
In machine learning applications, that sort of provide the practical motivation for this. How is it? You probably have to sort of, you're given a bag of data, you somehow have to translate it.
Yeah. Yeah. So okay, I'm not an expert in machine learning, but as far as I understand, it's what I described before. It's called the Vietoris-Ribs complex. It's the most basic thing. That you have to do a little bit of processing. You're given these points and you grow these balls around each point, and then you construct a graph out of that.
Is the size of the graph sort of polynomially related to the initial machine learning? The things that blow out or shrink enormously.
So I think the way that people think about it is that this is a way to dimensionally reduce your data.
So it might actually shrink.
Yeah, so you can shrink it, but in such a way that you preserve essential features.
That means that hardness in terms of the input smaller object does not necessarily mean hardness in terms of the initial input length of your machine learning problem, which was much bigger.
Yeah, no, I mean, so the points, so the size of the instance will be the number of points in your data cloud. It's just when you grow these epsilons, what you do is you're connecting points with edges, right? And then you have that graph whose number of vertices is the amount of points you have, and the live is potentially some very high dimensional space.
Are there practical applications where you have this kind of indirect formulation problem where the input is small, but the complex that you grow is exponentially?
Yeah, absolutely.
But not the one we just discussed.
Well, so generically,
What's
if you're building a simplex out of points, right? So what is a simplex? A simplex, you have to choose k number of those points, you take the complex whole of that thing, right? So you have n points, you have potentially 2 to the n. So it grows, it naturally grows exponentially the way that the triangulation of the space grows exponentially, unless you tame it in some way. Okay, sorry, let me move on quickly because I'm running out of time, I see already. Okay, so homology is just in your algebra. What it amounts to is finding that something called a Smith normal form of these boundary operators, which are sparse operators with entries 0, plus, and minus 1. Okay, trivial, you just do it. The problem is that the size of the matrices are level k are n to the k times n to the k minus 1. So when k is order n, then you have a problem. Okay, so you have your chain, which is length n, and I ask you, because I'm evil, I ask you, find the host exactly in the middle of this chain, so n over 2, and then you're screwed, okay? All right. So the question is, can quantum mechanics help with these exponentially large matrices? Okay. So put everything I told you about simplices on hold, and now we're going to do some review some complexity theory, as you all know. Let's define QMA1 that Harry asked before. So here's a formal definition. I just copy pasted from the original paper, so it's correct, and I don't have to take responsibility. But let me just, in terms of like a picture which I prefer. So it's the class of problems which, if there's a yes instance solution to your problem, you can verify this with probability. There exists a witness W here, such that you can plug it into the circuit, which is generated, is uniformly generated in polynomial size and so on. And you get with probability 1 that yes, it's a yes instance, and if it's a no instance, there's no witness such that well, you'll get one only with a low probability. So for all witnesses that someone could give you, you measure 1 here with probability less than a third. Okay. So this is how QMA1 is defined. It's the same as QMA, except that here there's a probability 1 instead of the parameter, instead of the completeness parameter, which we usually set to 2/3 here, set to 1. Another kind of observation is that it depends on the gauge set G. Okay. So you have to choose some universal gauge set and define your class with respect to this. So in QMA, this makes no difference. In QMA1, it's not clear. Okay. Okay. Final observation here are 2 qubit gates and 1 qubit gates. So a standard choice was used originally for constructing QMA1 circuits is to take the Hadamard plus this T gate plus a C0. Okay. We don't like this. We don't like this because it has a square root of 2. And we don't like it because it has an imaginary number. So I'll explain why later. This is bad. Okay. So, however, luckily in 2003, there was this paper that showed that there's another universal gate set that you can use, which is only C0 and a 1 qubit gate U, which has real coefficients. As long as this thing, as long as U squared is basis changing. So it kind of creates superposition on the basis states. As long as you have that U, you can combine with C0 and you have a universal gate. So what we're going to do, for reasons that become clear later, I'll use this gate, which, as far as I know, I haven't seen in the literature. It's called a Pythagorean gate for obvious reasons. So the reason why 3, 4, 5 up here is because you want it to be unitary. That is ensured by this old theorem by Pythagoras. And furthermore, you have here rational coefficients. So these, and they're real, rational. Okay, so this is good. I like this. All right. Okay, let me just review what quantum K-set is. So quantum K-set was defined by Gravi in 2006 as the quantum analog of K-set. And here you're given a bunch of projectors pi A. Okay, you form this Hamiltonian, which is the sum over all projectors. So these projectors are act on n qubits, they're k-local, and the number of projectors that you're given is polynomial n. And you ask the question, is there a state such that satisfies all the projectors? That would be a yes instance. Or if there isn't, then the expectation value of this Hamiltonian on any state will be bounded below by epsilon. Okay, so this is a promise that you're given on the problem. Okay, so the theorem that is fundamental here is that quantum force-sat is QMA complete. So this was proven by Bravi in 2006. Some details were improved later by Gosset and Gage in 2013, and we actually also write it down to 3-SAM. So I'm going to use the results of 4-SAM. All right, so I'm going to overview a little bit how this construction goes, because I'm going to repurpose it later for our proof. Okay, so it uses this kind of ideas of Feynman and Kitaev to build these, to encode the computational history of a circuit inside a Hamiltonian. Okay, so given a QMA1 circuit where made out of these C naughts and my Pythagorean gate U, in my case, what you do is you construct a certain Hamiltonian that depends on all these gates. So U is drawn from here, from the circuit, in such a way that if there's a yes instance to my original QMA1 protocol, then there's a certain state called the history state, which has zero energy with respect to this Hamiltonian, which means that because these are projectors, the only way this can be zero is that if every term is zero, okay, which means it's frustration free. Okay, because each of these guys is positive semi-definite. So the only way it can be zero is if each one of them vanishes. And if you're in the case of no instances, then the expectation value of the Hamiltonian is bounded below by epsilon, with epsilon being 1 over poly n. So here's a picture of that. You can follow this. In the case of yes instances, the energy, the lowest eigenvalue of this Hamiltonian is exactly zero. In the case of no instances, bounded below by epsilon. Okay, so the structure of the Hamiltonian has this form. There's an input Hamiltonian, a clock Hamiltonian, a propagating Hamiltonian, and L Hamiltonian. I'm sure you all seen this, familiar with it. So, okay, it gets a little nasty, but so this is a modification of Kitaev's Hamiltonian, which has a clock which is a little complicated. So it has 4 possible states. Let's call it unborn, active 1, active 2, and dead. And so the reason, some technical reasons why this clock is used. To reduce the level of locality from 5-SAT to 4-SAT. Anyway, but you take the formulas from the paper, and the important thing is that the dependence on the circuit gates appears here in this propagating Hamiltonian. Okay, and there's these U's here. Okay. Okay, and it's easy to see that this is an instance of quantum K-SAT because all these terms here are projectors. You can use. Using the fact that U is unitary, you take the square of this, you find that it's itself. It's a projector. Okay, so bottom line is that the computational history of the QMA circuit is captured by these Hamiltonians here. Okay, so you have to choose your gate set. I'm going to choose C naught and this U, or U hat. And then there's this clock part that just, doesn't depend on the gates. And what you see is that these are projectors and they're projecting onto these states, onto the orthogonal space of these states. Okay, so these are the states which have eigenvalue 1 under the corresponding projector. Okay, the orthogonal must have 0. Okay, so I'm just collecting all the projectors that appear. Okay, so now we come to our reduction, our construction, which is the most delicious part of the talk. Okay, so what is the idea? So the idea is the following. We want to identify, so what are we aiming to do here? We are aiming at encoding the QMA verification protocol inside a space such that that space has holes of a certain dimension if and only if the QMA1 protocol accepts. Okay, that will show that our problem is QMA hard. Okay, that's the goal.
Is this the decision problem? Or?
The decision problem, yes. Okay, so the idea is we're going to start with a space like this, you can think of it as a Swiss cheese, with a large number of holes, 2 to the n number of holes, where n is the dimension of the cheese. And then given an instance of the quantum force-sat, what is quantum force-sat going to do? It's going to fill in these holes. Okay, every projector is going to fill in some holes. And you should think that you're not filling in the holes, classically. you're filling the holes in kind of superposition. You're doing topology here. So you're deforming everything, and a hole can combine with another hole, the orientations. Yeah, it's topology plus quantum mechanics, so it's not very intuitive. But that's what this is not an accurate description. Okay, and so we're going to fill in these holes in linear superpositions in such a way that the remaining holes, at the end of the day, once they use all the projectors, there are remaining holes if and only if they're satisfying solutions to quantum force n. Okay. Furthermore, we'll make sure that the counting works out correctly, so that the decision version works, but also the counting version works. So the reduction is parsimonious. Okay, so let's go back to this table. So what we have to do is we have to identify these holes, okay, in our G's, and they're entangled in some way. I'll describe. Okay, so first step, we have to create the G's and make the holes. So this is how the G's is created. So this goes back to the example I showed before. Consider n disconnected triangles. Okay. So these will be my n qubits. Okay, my Hilbert space is 2 to the n dimension. Now consider the independence complex of this graph. Okay, so I have to look for all one independent sets. There are 3n of them, 2 independent sets, 3 independent sets, and so on. Okay, and then I compute the homology. So I basically look at those boundary operators and do the kernel mod the image. And what you find is that the space has one zero-dimensional hole. What is a zero-dimensional hole? It's just the number of components of the space. So the space is connected. Okay. Then another non-trivial homology group appears at dimension n-1. So it means that there are n-1 dimensional holes. Okay, and there's an exponential number of them. Okay, that's just because there's an exponential number of independent sets of size n here. Okay. All the other homology groups are 0. Okay, so this is perfect because this thing here will be my Hilbert space. I gotta ignore this connected component. It's just telling me that it's one Hilbert space, not 2. So this cheese here is not an accurate representation of my space. Do you know? Can someone point out why? An obvious reason, apart from the quantum superposition of holes. This picture here versus this. This has 2 connected components, and this has 1. Okay, all right. But this was the picture with the highest resolution. Okay.
You glue the 2 pieces.
We can glue them together. Yes. All right. So step 2 is we have our Hilbert space, and we want to now eliminate. We want to take states out of the Hilbert space according to the projectors. What that means is that we have to fill in these holes according to how quantum K-stat instructs us to do. So let's bring it down to Earth. Let's do 2 qubits. So okay, 2 qubits. Then this independence complex I showed you before. There it is. And so indeed, at c to the 2 to the 2 times 2, 4. This is the 4 holes that we saw before. Okay. So I have to choose a basis. So I'm gonna for these holes. So for example, A2 x1, or let's start with this x1 x2 x2 a1 a1 a2 a2 x1. This is my 0 0. There are 4 states. I'm gonna label them 0 0 0 1 and so on for obvious reasons. And so this is my one-dimensional hole here, and the other one and so on. Okay, so here they're depicted. This is my, I'm going to call this my computational basis of cycles or holes. Okay, this is 0 0, this is 0 1 1 0 1 1. This is just labeling for now. Okay, now let's consider the classical projector this. So this is one of the things that appears in that table of quantum K-stat. I want to project into everything which is orthogonal to the state 0 0. Okay, that will be a satisfying assignment to this instance of quantum K-stat. So that means if I go back here, this hole, which is 0 0, which is surrounded by this red thing, should not be a hole. How do I get rid of a hole? I just fill in this face. Okay, so I could just fill it in. So meaning I add to my simplicial complex an extra element whose boundary is this red line. Except that you have to remember that you're working with a simplicial complex where you're only allowed to use triangles or higher dimensional triangles. So I cannot fill it in as a square, but I can put an extra vertex in the middle, connect it in this way, and now this hole disappears. So basically the hole that is around, I can shrink it now to 0. So you say it becomes homologous to 0. Okay, it's the boundary of something where that something is the sum of these 4 two simplices. Okay? Yeah.
Like a pyramid.
No, this is all 2-dimensional.
Oh.
two-dimensional. So the boundary is a one-dimensional, so the interior is two-dimensional. I'm filling it just as, this is a slice of cheese. Okay? Yeah.
Of course. Does that mean that you have to somehow produce another graph?
Yes, exactly right. Exactly right. So what is that graph? It's this. So it's very simple. So you basically reverse engineer. You have the collection of independent sets. So you ask, what is the graph that will give me this? Is this very easy? Okay. In fact, there's a logic to this. So this is, you think of this as 0 and this is 1. Huh? Yeah, it took time to find it. But this is 0, this is 1, this is 0, this is 1. So you look here, you have a 0, 0, so you connect the 1, 1. Yeah, so you can think of this like a machine that's connecting. Anyway, this intuition will break down. You shouldn't learn the hard way, but okay. Okay, so let me just say from the point of view of Hamiltonian complexity, what we're doing is we're considering something called the, you can think of it as a system of fermions moving in this graph. So you can put a fermion here, 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 because they're fermions that don't like to be together. And so that corresponds to choosing independent sets. By adding this thing here, I'm allowing for the fermion here and the fermion here to interact with one another. So we call this a mediator. So given some forces. What these forces are doing is they're lifting some energy, some states that have 0 energy to lift it up. Okay, and that is analogous to taking things out of the homology. I'm running out of time. Very sorry. Let me move forward. Okay, how much time do I have left? We started a couple minutes late. Okay. So how much? Okay. All right. So what did we just accomplish? So oops. Yeah. So what we managed to do is to fill in the whole 0, 0. So like this one here, one of the terms in the clock. Okay. Why? Because that state, which is at the state 0, 0, which is identified with this particular cycle in my simplicial complex, is no longer part of the homology. Homology used to be 2 to the n dimensional. Now it's 2 to the n minus 1 because I got rid of this guy. Okay. Well, in the example I gave, it was 4-dimensional. Now it's 3-dimensional by adding this action. Okay. So I think you can believe me that 0, 0 and all the guys which are classical like this are pretty straightforward to do. So for example, if you want to lift this state, you just take 4 triangles connected to 1 mediator. You're done. So this is simple. 1, 0 is just a relabeling of things. So it's the same thing. And the ones which are 1 triangle, they're even easier. Okay. So we got this part of our list. So the fun really begins when you try to fill in entangled holes. So let's look at the same example. So this is the same simplicial complex I drew before, just shown differently. Okay, you kind of turn it around and flatten in one of the faces that was sticking out. And the reason you do that is because now this hole, you can identify 0, 0, minus 1, 1. So you go in one direction, and you go in the opposite direction. Passes through all the vertices in your simplicial complex. And you have to fill in this face. So you say, well, fine, I just put a vertex in the middle, I connect to everything around, and then I fill in that face. But that's not correct because that would fill in too many things. Because it goes through all the vertices. If you do that naive thing, you will be filling these holes here. And I only want to fill this hole. Okay, I want to eliminate one element from the Hilbert space, not all 4 of them. Okay, so what you find is that 2 mediators also don't work, but you have to use 3 mediators. Okay, you connect them this way, there's a triangulation, and this works, and you go back to the graph, and that's the graph. There you go. Okay, this took months to get. Once you think about it in the right way, it's obvious, but that's always the case. All right. So another way of thinking about this is you have these 2 triangles, and you're connecting them in this complicated way, which is lifting, which is in the ground state. The thing that is remaining is the state 0, 1, 1, 0, and 0, 0 plus 1, 1.
Doesn't this interfere with all the things you have added previously?
Yeah. What do you mean, interfere?
Because you already added points connecting these 2 triangles.
Yeah.
Now you're adding more stuff.
I'm looking at, so you think of it as I have these n triangles, and I say, imagine these 2 triangles are connected via this unitary gate. What do I have to do in order to realize that gate between these 2? And then I'm looking at some other 2. For a general circuit, everything is going to be touching with each other. So I'll have to connect all these triangles in combinations of these ways. But these are the basic gadgets that I later have to put all together. And they're going to interfere. And that's what makes the problem hard. Okay, so what we did is what we just said. I constructed a space, or rather, a graph G2 prime, I'm calling it, this complicated interaction, such that the homology is no longer 4-dimensional, it's 3-dimensional, and it's precisely these states. Okay, so the state which is excluded is the 0, 0, minus 1, 1, which is precisely the state here, which is which this projector, takes out of the space of satisfying solutions. So we have a 1-to-1 map between space of satisfying solutions from the simple projector onto this homology. Now we have to generalize it to all the gates and to arbitrary m. Okay, so first part done, and I'm 2 minutes behind. Okay, so this is my progress card. So we did this, and now we did this. I haven't told you how to do tensor products of things, but believe me, that's simple. Okay. So we have to do this. So it's a 3-qubit entangled gate, and we have to do this one, which is also a 3-qubit entangled gate. Okay, tensor products race. Okay, starts getting more fun. So three dimensions, so 3 qubits. So we need to fill in 3-dimensional empty spaces inside this 2-dimensional capsule that is surrounding it. We need to fill this in. For example, if we want to lift this classical state. So that one is easy. You just fill this with tetrahedra, with solid tetrahedra. Okay, you can do it. The difference, this entangled guy, not so easy. Okay, but you can do it. You need 5. The best you can do, I think, is 5. You need 5 mediator points. You connect them all in some way, and you do it. Okay, and you get this. Okay, so this is the second part of what we needed for the C0 when it acts in 3 qubits. Okay, so you start seeing a pattern. So if you remember, the one for 2 qubits, G2 prime was kind of the upper part of this thing, and now you have the lower part of this thing when you add 1 more qubit, and you're like confident that, okay, good, I'm seeing the pattern, so it's gonna work out. Okay, so we just left with these 2 states, okay, which are the Pythagorean states, the ones corresponding to the Pythagorean gate. Okay, so indeed, if you follow the pattern of what I just said, you get you have to construct. So here's where you see why the 5, 4, 3 are important, okay? Because we don't know how to add cycles with square roots of 2 or with i's, okay? I don't know how to do it. But with integers, I do it. I just go 5 times around. So. Okay, so as I said, these integers are important. So the strategy is you take this cycle, which are each one of these is this double pyramid. Okay, you have to take 5 copies of one, 4 copies of the other, 3 copies of the last one. Then you glue them in some way, like this. Again, not an accurate representation, but not too far. So you glue them through some common, subspaces, and you fill it up with solid tetrahedra. And because you already have some experience looking at the previous cases, then you just guess the answer, and what comes out to be is exactly what you would expect. Yeah. And it's not clear that you can do a lot. So what is this? This is the graph whose simplicial complex. So there are 3 hidden triangles here. See if you can find them. Well, there's a 1, 2, 3. That's 1. I know because I labeled them this way. And then 4, 5, 6, 7, 8, 9. Here. Okay. All the other guys are mediators. So we have in total 90. So there are 81 mediators.
They don't get along very well, it seems.
They don't get along very well. And but this is the answer. And actually, this is not even the brute force method. The brute force method would just be a blob of blue. This one you can see some structure. And so all these edges are just given interactions between these 3 basic units. Okay. And the count. So why does this crazy thing come out? It's because
you should draw the complement of the graph.
it won't help you. I tried. Well, the degree here is not so high. So if you look at this, it has a degree 6 or something 7. Some of them have very high degree. But if the complement, it doesn't really help. Yeah. So we need to check, because if you get such an insane answer, you cannot trust it, right? Okay. So we need to check that what do we need to check? That the only hole that we filled is this hole. Okay. Okay. The problem is not an NP. So the number of simplices correspond to the graph. So there are 90 vertices, as I said, 581, 1 independent sets, 2 independent sets, and so on. Okay. You build this crazy simplicial complex, you plug it into Mathematica, you wait 20 hours and 40 minutes, and you get yes. And it's unbelievable. So I should point out, this is a 3-dimensional space. The simplicial complex is 3-dimensional. And you just trying to prove that there's one 2-dimensional hole, only one in this space, but it's the particular linear combination given by this guy here. The proliferation of mediators has to do with the number 5, 4, and 3. Basically, you have 5 copies of this guy. This guy has 8 faces. So you have 5 plus 1, 9, 3, 12 times 8 times 12, 96. Yeah, you have 90 vertices, more or less. Maybe you can do better, but you have to think, and we don't like to think. So, and then the great number of edges comes from the fact that you added so many mediators that now you have enormous number of independent sets of size up to 90. And that will give you holes of higher dimension, but you don't want holes of higher dimension. So to eliminate those, you have to connect all the mediators to eliminate all those independent sets. So we're kind of stuck with this. Maybe we're going to improve a little better. Anyway, so in case you fell asleep and you want to know the punchline, this is okay. So putting all these gadgets together, I'm sorry, I'm about to finish. You prove the theorem that homology is QMA hard. So along the way, we prove 2 other results, which are here. I can tell more about later. I'll skip it. So summary. All right. So homology is quantum mechanical. I argue that based on the physics of supersymmetric systems, and it's all paper by Witten. That should be the expectation. And you can prove this more rigorously by showing that the problem of homology is QMA hard and containing QMA, which I didn't explain that's containing QMA, but that's the easy part. So that's easy to prove, provided you give a certain promise of this operator here. But I can tell more details if you're interested. Okay, so outlook. One of the questions is what are the consequences of this for the Betty number problem? That I began with, the applications to estimating Betty numbers and the quantum algorithm. We believe that this problem, you can show this problem is DQC1 hard, and therefore it cannot be quantized. So we had partial progress with Chris on this, more. And I believe there are many more problems here lying at this intersection. This was just kind of the simplest one. So you should go through the list of other 34 problems in this paper, and you have 34 projects there. Okay, so join us when you need help, and it's fun. Yeah, thank you.